All right, good afternoon. Let's see, where is okay, we stopped here last class. Some of your findings for power equations. Let's continue on from there. We look at derivations of REQs for a resistive network. Okay, all right. So when you perform analysis involving resistors in a circuit, it helps if we have if you can apply Ohm's law directly, right? So let's consider a large resistive network comprised of n number of resistors, and they could be configured or connected in multiple different ways, right? Some of them could be in series, some of them could be in parallel, some of them neither in series nor in parallel. So as far as the source goes, what the source sees is just one single resistance. The source does not know whether they are one or whether they're 10 or 100 or 1,000. It only sees one single resistance. So let's say we connect one single resistance to a pair of terminals at the source. Apply Ohm's law. We know the voltage, we know the resistor value, and we can find the current that's being supplied from the source. Now let's add one more resistor to that first initial resistance, so R1 and R2. Well, depending on how we connect it, we saw in the previous lecture, we can apply Ohm's law and solve for that circuit, right? So it does not matter how many more resistors we connect to it, but we can reduce, sorry, not reduce, but the source is only seeing one single resistance. So when we perform theoretical analysis, we have developed methods where we can reduce that resistive network down to one single resistance. Two of them you're familiar with, connecting resistors in series and connecting resistors in parallel, right? There's one more that we'll look at today. And then we'll also look at the derivations for the series and parallel. Also, another important point to keep in mind is this REQ, which stands for the total equivalent resistance as seen by the source. Okay, total equivalent resistance as seen by the source is different between any 2 points in a resistive circuit. So as an example, let's say a circuit has 5 nodes. A, B, C, D, E. Well, if you measure resistance between A and B, you'll obtain a value. If you measure resistance between B and C, you'll obtain a different value. Between C and D, between D and E, or A and E, between any 2 of these nodes, you'll get a different value every single time, depending on how the resistors are connected. So the resistance between any 2 nodes, the REQ, between any 2 nodes depends on the resistive connections. It will not be the same. Okay. Because the key point to remember from previous slides, if you have a parallel resistive network connected in there, it pulls different power than if it's a series connected resistance. Okay. So if you look at a circuit from the perspective of 2 different nodes, then the resistors will be different. Hence, the power required from the sources is also going to be different. The one advantage is that the single REQ retains the same properties of a linear resistor. So it is a linear resistor where V voltage and current I are proportional to each other. If either one of the quantities increases, the other quantity increases or decreases. Okay, so it's a linear device. All right. Series connection of resistances. We already know this. You have already studied this in the past. You may or may not have studied the derivation though. So derivation for this is from Ohm's law. So you have a voltage, you have a current source supplying current I through a series connection of resistances, causes a voltage drop to appear across both resistors, VR1 and VR2, V1 and V2. We apply KVL. Sum of both resistors is equal to the total voltage being supplied from the source. All equations are based on law of conservation of energy, KVL, KCL thing. So total voltage is V1 plus V2. Apply Ohm's law, you get I times R1, I times R2. I is common, take it outside. And we can write our EQ is R1 plus R2. Okay, R1 plus R2. So mathematically, we can state let's just keep. So mathematically, we can state Req for series connection of resistances is simply the sum of all those resistances. Add them all up. Doesn't matter what values they have. They could have the same values. They could have different values. It's simply matter of summing them all up. Okay. Important takeaways for a series circuit are these. In a series resistive circuit, current is the same. There is no other pathway for the current to flow. However, voltage is divided. Okay, voltage is divided. So the total applied voltage is split across that series connection of resistances according to the ratio or according to the value of those resistors themselves. We can derive a shortcut technique to calculate these voltages. It is known as voltage division principle. And that is based on Ohm's law. Let's take a pause. Let me know if you have any questions. So far, so good. Okay. All right. Let's look at parallel. Parallel is the same. Now we have a voltage source. We're applying a total current. Current splits into I1 and I2. Total current can be derived as a sum of I1 plus I2. Apply Ohm's law, we get V over R1, V over R2. It's a parallel network. So in the parallel network, voltage remains the same, doesn't get divided because it's the same two nodes. So parallel resistive circuit or parallel connected resistors. Parallel connected resistors, voltage remains the same or voltage is the same for all components. However, the current is divided. And that current is divided depending on the value of the resistors themselves. The lower the value of R, the higher the current. The higher the value of R, lower the current. Inversely proportional, right? So, yes. This is simply showing the derivation for REQ. Yeah, for REQ. And another technique we can derive for this is current division principle. These are all derived from Ohm's law. They're simply shortcuts. Okay, they're shortcuts that allow us to quickly determine the voltage or current through any particular resistance or through a current through a resistance. So coming back to this derivation, we have V over R1 plus V over R2. Take the V outside, it's common, and we find this term is the reciprocal of REQ. The total I, total current flowing through the circuit, must equal the total voltage applied to that circuit. And logically speaking, that R in that Ohm's law will be the total equivalent resistance of that entire network. And so it turns out that REQ here is the denominator. So 1 over REQ is equal to that term. And hence, when you flip REQ is the reciprocal of the sum of the reciprocals, as indicated by this equation. Okay. And again, it's all derived from Ohm's law. Ohm's law, KVL, and KCL. Okay. Now, of course, why do we do this? Well, because in real life, if you have a source and you connect a circuit to it, if you have a load connected to it, the source does not see hundreds of thousands of components. It's only seeing one single component. It's only seeing one load. That's it. It does not see anything else. So we need to perform theoretical calculations on our circuits in order to determine that one single resistance, right? And so you have seen that, you've done this. We'll go over for a quick example. In this case, if you're trying to reduce the circuit down to one single resistance, we start with the branches that we can reduce. Right here and right here. And so that gives us REQ in this case is measured only between these 2 points. This turns out to be 2.48 K. This one comes out to be 2.5 kilo ohms, 5.1 kilo ohms. And then those two combine to form 1.68 K, with the result being that we have one single REQ value, which turns out to be 4.16 kilo ohms. So to analyze this circuit, we can reduce the entire resistive network down to one single equivalent resistance. Now, no matter what voltage we apply, we can calculate the total current supplied by the source. And thus, we can calculate the total power that needs to be delivered by the source. Okay. And that's why we need Req. You can use the same laptop adapter that you have now, USB-C, to charge your smartphones. You can use it to charge your tablets, and you can use it to charge your laptop. Okay. All three devices require different levels of voltage and different levels of power. So the circuit designers will design instruments to fit within that power requirement. Okay. The total equivalent resistance will never be more than what a system source can supply. All right, let's take a pause. Let me know if you have any questions. Yes. Kilo ohms, yeah. Question being asked is about milliamps and kilo ohms. They should all actually have ohms. In all resistances, they should have ohms. Resistance, by the way, is one of the only quantities I can recall that has a Greek symbol for its unit. All others use letters. Volts uses V, amps uses A, power uses W, charge uses C, capacitance uses farads F, inductors use Henry H. Resistance is the only one that uses omega. Okay, all right, so no questions. Let's move on to something like this. The question is, are there some circuits that are difficult to reduce? The answer is absolutely yes. Real life circuits are very difficult to reduce manually. You must perform some tricks and transformations. So let's first look at just standard, okay? We have a circuit comprising of 5 different resistors, 1, 2, 3, 4, 5. There are 4 nodes in the circuit, A, B, C, D. If we wish to find the Req between any 2 nodes, we first start with a resistor that is connected between those 2 nodes. So let's take the easiest one, RBC. If we have RBC, which resistor is connected between BC? It's R3, right? R3. So R3 is connected between B and C. Now, here's the important concept point that we have to apply. You have 2 nodes in any circuit. Well, anything that is connected between 2 nodes is said to be in parallel. So what else do we have connected between B and C? If we look at the circuit right here, we know R3 is connected, yes. But let's look at the other pathway. The other pathway goes here, and the other pathway goes down. So we start at B and go around the top. We come back to C. Anything that is there in that pathway, doesn't matter if it's 1 component or 2 or 2,000 or 200, they're all in parallel between B and C. Or not all. All of them combined is in parallel with B and C. And the same thing with the bottom loop. So anything that is in that bottom pathway is combined as one single Req and is in parallel with R3. So I can represent this as one single resistance. Now, the pathway in the top only has 2 resistors. The pathway in the bottom only has 2 resistors. So makes our job easier. But the concept still applies. And you will see that in the next when I try to find resistance between RB and A, or RAB. Okay. So what can we say about the resistor on the top that has R1 and R2? They are absolutely in series because they're connected only a single node at A, and there are no more than 2 connections at that node. If you have more than 2 connections at a node, that means they are no longer in series. But R1 and R2 are only connected at A, and there are no more than 2 connections. And so R1 and R2 are in series. And so I can write R1 plus R2. Okay, R1 plus R2. Same thing at the bottom. We have 4 and 5 in series. And so I can write R4 and R5 are in series. Okay. And then, of course, those 3 are in parallel. So that one is rather straightforward, not that difficult. But how about RAB? RAB. What do y'all think? That's a good guess, but not quite. So let's draw the circuit. We have this around. We have 2 resistors here, 2 resistors here, one in the middle, and then A is at the top. B is on the left here. I'm trying to measure the resistance between A and B. So remember the concept, what do we say? Anything that is connected between 2 nodes is in parallel. So the first thing that we have between A and B is R1, right? So let's say this is A and this is B. Okay, what do we have? One single resistor. The rest of the circuit, all of this, is in parallel with R1. Even if we can't, if my brain cannot visualize it, but technically I know it's those same 2 points, A and B. That means whatever is connected between A and B is in parallel with R1. I just don't know what that is yet. And so we'll determine it. Okay. So let's start by just labeling everything. So we got R1, we have R2, we have R3, R4, R5. Okay. Now, if we start at A, what else do we have at A? R2. So we have R2. And then we are starting at A and making our way to B. So what do we have? We have R3. And R3 goes to B. You all with me so far? Right. Okay. Right. So now, what else is remaining? between R2 and R3 is node C, and we have R4 and R5. Sorry, wait, R2 and R3. But yeah, R4 and R5 that are in series. So we have that because, actually not from there, from C, node C to B. This is node C, right? So from node C to B, we have R4 and R5. At node D, between 4 and 5, there's nothing connected. So 4 and 5 are in series. We can combine it together to form one single resistance. Okay. And now it's easy to visualize what my Req would be. R4 and R5 are in series. It's in parallel with R3. And that would be in series with R2. And finally, that entire combination is in parallel with R1. So let's take a break. I mean, not break. Let's take a pause. You think over that. Let me know if you have any questions. Yes. See, the question being asked is about R4 and R5 and how they are connected. So they're not passing through anything. Node C is simply a junction point for those three. And if you look at the circuit above, we have R2. So we have R2, R5, and R3 connected at node C, which is like right here. So R2, R3, and R5, R4. So I labeled it incorrectly. This should be R5, and then this would be R4. That would be more correct. Does that answer your question? Okay. Again, the goal of the technique or any other technique is to simply find Req between any 2 points. So in this case, if it's A and B, we start at A and we make our way to B. It depends how many pathways we have, right? That makes sense? Need more of a pause. So B and C, yes, I simply reduced it and drew it because they're all in parallel. Because everything, so I started and observed this pathway. So I want to measure between B and C. The first connection is, of course, the direct resistor R3. And then we start at B and we make our way around the circuit to C. And the same thing on this side. And that's what we did for RBC. Okay. All right, so there's another kind of transform that we can do. And that applies when resistive elements are connected in a triangle form. And we can change it into a Y form. And the name of the transform is delta to Y. This is a more appropriate topic for three-phase systems because that is where we would perform the configuration. But here we'd like to give a small introduction. We can have delta to Y or Y to delta. The reason delta is because it looks like a triangle. So let's say I have we have our three resistors R1, R2, and R3 at the top, right? R1, R2, R3. Now the way they are connected, and I'm going to label this node A, node B, and node C. In the original circuit, that node A is drawn as a long line. but long line is nothing but a dot. This is R1, R2, and R3, and ABC. And you can change this to still the same thing, A, B, and C, the same three nodes. Because these three resistances. And let's call them Rx, Ry, and Rz. Okay, X, Y, and Z. So there are, of course, derivations that go along with this, but we are not going to cover that right now. Simply giving you the equations on how we can do this transform. Okay. So we have Rx, Ry, and Rz. The denominator is the sum of the three resistances. So R1 plus R2 plus R3. I'm going to be a little bit lazy and simply paste it. And the numerator is the product of the two resistors that were connected at that node. So if you're trying to find Rx, Rx is connected at node A. And in the original delta, node A has R1 and R2. And so this is R1 times R2. That's how we perform this transform. So knowing this now, what is in the numerator for Ry and Rz? Let's look at the node where Ry is connected. Then take that node, go to the original circuit diagram, and then which two resistors are connected at node B? Any answers? R1 and R3 or some murmurings and mumblings? How about RZ? There's only one combination left. R2 and R3. So we can calculate or can easily calculate the values for the resistors in a Y combination. But now let's see how this would help us in reducing the original circuit. The original circuit, let me draw it out like this. The original circuit, I have R3 here, right? This is B, this is C, this is R3. Oh, not 3, 4. 4 and 5. This was our original circuit. So now if we transform this, what do we get? The nodes are still the same, A, B, C, and D. But now the resistors are transformed. We got Rx, Ry, Rz. Let's call this Rm, N, and O. RO. And now that we have a transform, we can see Ry and M are in series, Z and N are in series, and then everything else. And then those on the left and right are in parallel. We reduce it down to one single REQ easily. Let's take a pause while you think over all of that. Let me know if you have any questions. Does everyone see the reduction? If you wish to find the REQ between A and D, let's want to find rad, then this is what we do. Okay, delta to Y transform, and then we can easily reduce the circuit between A and D. What difference do you notice between the two circuits? Other than, of course, the schematic looks different. That is very true. You have resistors in parallel. Well, first they're in series. So Ry and M are in series, Rz and N are in series, and they're in parallel. But look at the total quantity of resistors. There's 5 in the original and there's 6 in the transformation. So again, this is simply the fact that we are performing a theoretical transform, right? R3 appears in both triangles. And hence, we have 6 resistors, 3 at the top, 3 at the bottom. And you can actually create this circuit in the lab. And you can find the values for resistors on both sides. Well, you don't even have to go to the lab. You know how to use LT-Spice. You can do so in LT-Spice also. Apply a voltage, 1 volt or 10 volts to the circuit between A and D. The circuit on the left and circuit on the right. And look at the total current being supplied by your source. It will turn out to be the same. Okay. All right, 10 minutes left. Yes. Okay, so the question being asked is if the bottom one did not form a triangle, would we be able to use and transform this? The answer is no. We would not be able to transform. We would be able to transform the top. Yes, we can do so. Yeah, we would be able to transform the top, but not the bottom. And remember, when we were trying to find RBC, we said 4 and 5 are in series. But if we want to find RAD, we are measuring at D. So 4 and 5 are no longer in series. It's an important point to remember. Okay, if you're trying to find RAD, then we cannot treat 4 and 5 as being in series because you're measuring at that node. These seems like very small things, but when we get to work with circuits, performing circuit analysis, and we're trying to reduce a circuit, the knowledge of these concepts is very important because you try to reduce a circuit, and then if you don't apply these concepts, answers would be incorrect. Okay. All right. Let's look at a few other topics. Okay, so in a energy system, in a system that is either supplying or receiving electrical energy, a transform is taking place. Electrical energy is being converted into other forms of energy, optical, thermal, mechanical, and so on and so forth, depending on your application. We have sources, voltage sources and current sources, and we have passive components like resistors, capacitors, and inductors. Now, when we perform theoretical calculations, we always assume that we are working with ideal components. However, ideal power sources do not work in real life, right? If we take a look at a voltage source, the resistance between its terminals will say it's equal to 0. So if you connect a resistor with 0 ohms to a voltage source with V, calculate the power, what do we get? Infinity. Same thing with the current source. Infinite resistance results in infinite power. This, of course, is not possible in real life. Okay, so we cannot simply use these models for real life. We can perform initial calculations, perform our theoretical calculations, but then we do at some point have to take into account practical limitations of real life components. And so ideal sources do not have infinite power capability. Okay. We can model voltage sources and current sources as having resistors in either series or parallel. So let's take an example of an energy source. That energy source can supply 12 volts at its terminals, and its practical rating for power, PR, is less than 100 watts, less than or equal to 100 watts. So it's like any other laptop adapter. You have a laptop adapter or a battery charger for your phone. Those have power limitations, power ratings. So let's say this is a laptop adapter. It can only supply 100 watts max. Okay. So it sustains 12 volts, meaning it supplies maximum of 12 volts and maximum of 100 watts. So how can we model such a power limited voltage source in real life? Well, in order to do that, we place a resistor in series with that voltage source. Okay, resistor in series with that voltage source. So real life voltage source will have a resistor in series with the source. So this is known as the source resistance. Okay. But why do we model it in series? Why not in parallel? Anyone? Why not in parallel? The answer is right there, right? You parallel, yes, you have it. Yeah, that is part of the explanation, yes. So in parallel, if you connect a resistor or anything in parallel to the voltage source, the property of a voltage source is it supplies its rated voltage between those two terminals of the output. So no matter what kind of resistances you connect to the output, it still supplies that rated voltage. So we cannot accurately model a voltage source with a resistor in parallel. We must show a resistor that consumes some of that energy inside it. And so we model it with a series resistance, RS, or source resistance, RS, for a voltage source. And so for that reason, if voltage is supplying some current, some of that power is consumed within itself. In real life sources real life sources or benchtop supplies are designed to compensate for that internal source resistance. Okay. So if it's 0.36 ohms, we can calculate how much power is absorbed by 0.36 ohms, and then calculate and design our power supplies in a way that voltage drop is accounted for. So instead of sending out 12 volts, it'll send out 12.1 or 12.2. And so that 0.1 or 0.2 volts drops across that internal source resistance. If it was 0 ohms, well, then again, if it's 0 ohms, then it's infinite power. So we can't model it that way. Okay. So you have a resistor in series with a voltage source. And then one last thing is that in order for maximum power to be transferred from the source to your load, the load resistor must match that source resistance. So maximum power is transferred only when the load resistance RL is equal to RS. And this is known as the maximum power transfer theorem. Okay. Maximum power transfer theorem. Maximum power is only transferred from the source to the load when both are matched. Okay. All right. Any questions? This is where we ended in the previous section. So this is where I'll stop or end class in this section also. We have like about a minute, less than a minute left. Okay. So quiz on Monday based on the material we have covered this week on Monday, Wednesday, Friday. And so, yeah, just prep well. And then we'll see you all on Monday. So have a good weekend. See you on Monday. There's no homework due this week or this weekend. If I do post a homework, it'll be due next week. All right.